A protractor lets us measure angles between line segments, but only if we have access to their intersection or the vertex of that angle. And it works by putting the vertex here in the center point of the protractor and then using this zero line as a reference along one of the segments. Then, depending on which way you're measuring, that zero line allows you to come along to measure the exact, well, within precision levels of the protractor, to measure the angle between those two segments. So let's draw a couple angles and then measure a couple of pre-drawn angles just to see exactly what this looks like. So to start, let's create a 60-degree angle from the horizontal, meaning that if I put a vertex here and I draw a horizontal line out from that, and the protractor creates a nice straight edge for us, I want to measure up from the horizontal 60 degrees. So I take my protractor, I put the center point on the vertex of the angle, and I allow my zero line to align with whatever reference I'm using. In this case, I'm using the horizontal line as my reference. I'm going to come up and look for 60 degrees. Oh, I started a little too high. But I'm going to put a tick mark out where 60 degrees intersects the perimeter of the protractor. And then I can take my protractor to connect the vertex of the angle and the dot that I made out here at 60 degrees. I won't go all the way out to go over my writing. But by connecting those dots, I've now created what is a 60-degree angle from the horizontal. What if I want to measure 60 degrees to the bottom or the south of the horizontal? So let's say this is east direction. Let's measure 60 degrees down to the south. Still put my center point on the origin, and I align my 0 point with my reference line. But now I'm coming down 60 degrees to the bottom. Put a little tick mark there where they intersect. And now connect these two dots. And that becomes a 60-degree angle now south of east. Let's draw a .30-degree angle, and let's make it east of south. So because I'm rotating 30 degrees from the south direction, I'm going to draw in my reference line now is going to be a south direction ray, we might say. And I'm going to measure 30 degrees east of that. So in this case, there's two ways I can do it. I can go to the origin and align my 90 and come down to 60 degrees. Or I can put my origin up at the vertex. I've got my 0-degree line on the south-facing ray, and I come up here to 30 degrees. Connect my dots. And now I've rotated 30 degrees to the east of the south direction. Let's just create a random angle. Draw a line here, and then randomly draw a line down here. And we want to measure what this angle is between those two. So I have to pick one of them as my reference, and it honestly doesn't matter. All it's going to affect is the orientation of the protractor. I put the origin of my protractor on the vertex. I align my 0-degree line with one of them. And I come out here and I realize that unfortunately my angle line isn't long enough to get out to the tick marks. So what I'll do is I'll just extend the line, because this ray goes on forever. I'll just extend it out so that it's accessible. I go back to my origin. And now I see that it intersects at 50 degrees and one tick mark over. So this is a 51-degree angle. If I want to measure the other direction, I put the origin at the vertex. I have the same problem with this line not extending enough, so I'll just extend it out a little bit so that it hits the perimeter of the protractor. And I measure now 50. Yeah, I guess I made a little error in the other one. This is more 51.5 degrees, so we would say maybe 52 degrees. This is not the most precise measuring instrument, so you are going to have some error, but that's the way that we would approach that. Why don't we draw two vectors now and just show how to add two vectors graphically. So I'm going to draw two vectors with the following directions and magnitudes. So I'm going to take vectors A and B and add them to find the resultant vector C. Vector A is a 30 Newton vector acting at 20 degrees south of east, and B is a 25 Newton vector acting at 40 degrees west of north. So I'm going to add A plus B, which means I'm going to start with the tail of A and go to the tip of A. And the scale I'm going to use is 1 centimeter is equal to 10 newtons. So let's find a place out here for the tail of A. And I'm going to go 30 newtons at 20 degrees south of east. So my reference direction is east, and I'm going to come south of that. So there's my east reference line, and I want to come down 20 degrees south of that. Now I'll extend this a little bit more just so I know I'm finding the right place. And you can use the graph paper as a reference too, but it's nice to sometimes have a line. So right there, I'm at the origin, I'm aligned at 0, and I'm going to come 20 degrees south. So right there's a tick mark at 20 degrees, and I've rotated south from the east direction. So I'm going to draw a light construction line along there. I'm going to measure it, so if 1 centimeter is 10 newtons, I have 30 newtons, that means I need 3 centimeters. Right there's 3 centimeters. That is the tip of A. And then I'm going to create vector B there. Its tail is going to be at the tip of A. So B is a 25 Newton force acting 40 degrees west of north. So in this case, my reference direction is north. So I'll kind of use these lines as a guide, and I'll just draw a parallel reference line parallel to the north and south grid lines of the paper. I could also mark, if I wanted to, I could mark a 90-degree mark, but it's a lot easier just to estimate by staying parallel to the graph lines. And I'm going to now come from north 40 degrees to the west. I put my protractor so its origin is at the tail of B. Go up north and 40 degrees west of north. There's 40 degrees. Draw my line connecting the 2 points. Light construction line. It's a 25 Newton vector, so I need 2.5 centimeters at my scale. Right there's 2.5 centimeters, so that is B. And now that I have them drawn in, I'll label them. This is vector A. This is vector B. And then C is going to be the resultant, and the resultant always goes from the tail of the first to the tip of the last. So I'll just connect tail of the first to the tip of the last. This is vector C. And I will measure its length first to find its magnitude. We'll put the 20 centimeter mark as the 0. And I'm seeing that it is 1.5 centimeters. So the magnitude of C is 1.5 centimeters, but 1 centimeter is 10 newtons. So we'll multiply that by, we want centimeters to go away, we want newtons to remain. 10 newtons is 1 centimeter. That means the magnitude of C is 15 newtons. Now let's find its direction. So this is one where I know for a fact I'm going to have to extend this line. I'll extend it out to where my writing is. But I'm going to measure the angle by putting the origin of the protractor at the tail of C, align my 0, and I'm going to come up and I go 10, 20, 30, and then I'm out to 32. 33.5 degrees. So this is a 33.5 degrees. Well, let's just for the fun of it say that both of these have 2 significant digits. That means this only has 2 significant digits, so we're going to report this as a 34-degree angle. So to fully describe vector C, we would say vector C is a 15 Newton force acting at 34 degrees. From the east direction, we rotate north. So it's 34 degrees north of east, and that's vector C. So that is graphical vector addition using scaled sketches. Good luck.